10. They ask us to describe the function g in terms of f in the following cases with c a real number, a constant real number. Okay, so we have different variations on f. So we have g is f of x plus a constant, or g is f of this argument x plus c, f times f of c times x, f of 1 over x, f of the absolute value of x, the absolute value of f, 1 over f, and the positive part of f. Okay, so all different variations over f. And so B and C asks us to plot these functions when f is x squared and when f is the sine of x. Okay, so I think the easiest way to describe this, or to show it to you guys, is to actually plot this function with x squared and sine of x, and then talk about what these operations on f do. Okay, so let's start with x squared. So in this case we have f of x is x squared. Okay, so I've copied here the different variations, and so you can see that each one of them does the different things. So the first one, this is 1, and this is f of x plus c, which means that this is x squared plus c. So I've chosen c equals 3 in this case. Okay, I've used Python script to plot this, but then you can use Wolfram Alpha again. To online to plot these functions. Okay, it's super easy to do. So okay, so in this case this is x squared plus c, which is in this case is 3, and the blue line is this function g, and the dotted the dashed black line is the original function f. Okay, and so this function x squared plus c, as you can see, this is exactly the same function as f. It is just shifted upwards. Okay, so you can think about it. If you think of, whenever we plug a value x here, I have x squared, but for g I have x squared plus c, so it's the same value as I had before, but with a constant. Okay, so for every x I'm just shifting the value a constant c, which is 3. Okay, this is easiest to see here at 0. So at 0 f has value of 0, x squared is 0, but then for g it's 3. Okay, so 0 plus 3, and then you do that for every other value, and you will end up with the same curve but shifted 3 units upward. Okay, so for 2 this is similar. In this case, this is what's shifted is the argument. So in this case what we have is x plus 3 squared. Okay, or c in this case, c. Okay, so what's shifted now is the horizontally. Okay, so you can think about the x-axis, this new variable, you can call it, let's call it z. This new variable is x plus 3. Okay, so this new function is just z squared, so it's the same function, as you can see, the same curve as the one, the dashed line, but it's just shifted. Why? Because x plus 3 is it's just this new variable z is the same as x, but as if we looked at it 3 units to the left. Okay, so you can think about it in other words, is if you want z to be 0, okay, then x has to be minus 3. Okay, so z is like kind of the same as x, but minus 3 in a sense. Okay, so always to the left. And if I had chosen a negative value for c, so instead of x plus 3 it had been x minus 10 or something, the shift would be to the right. Okay, so remember that if I sum something to the argument, the shift is to the left. If I subtract anything to the argument, the shift will be to the right. Okay? So, yeah, vertical shift, horizontal shift, and in 3, what we have is an argument. So this is f of c times c. So in this case, it's 3x squared, or in other words, 9x squared. And as you can see, what's doing it here is that the function gets kind of compressed. And why it's that is because now whenever I because for every small value of x, I now get much more of g, because it's multiplied by 9, so it gets higher faster than the original curve. But what's if you actually zoom in to this curve, you would see that it's actually the same as this one, but it's just that the x-axis has been compressed. Okay, so now in order to have the same value, you have to so for instance, if you have the value for x equals 1, is f of x is 1, so the x squared of 1 is 1. But for this new g, you would have to plug in 1/3 in order to have 1, right? So if I have, for an original value here at, let's say, 3, for instance, in order, so for in the black line, what I mean, so if 3 has this value in the black line, to have the same value in the blue line, I would have to plug 1/3 of 3, right? So I'm compressing the x-axis. And if instead of choosing larger than 1 number, I chose a smaller than 1 number, then I would have a stretching of the x-axis. Okay, and in this case, it doesn't matter if if c is positive or negative because of the function, but it would change if the function would be different. Okay, if depending on the function, if c is negative, then you can have an inversion around the x-axis. Okay, so for 4 we have f of 1 over x. So in this case, this is 1 over x squared. Okay, so this is 1 over x squared, so this is just 1 over x squared. And as you can see, this is kind of a very interesting function. What you have is an inverse function. So when x is 0, then now this function will be infinity because it's 1 over 0, and then it goes to 0 as x goes to plus and minus infinity. Okay, so incidentally, here in this case, we have 1 in 7 here. 1 over f of x is 1 over x squared. In this case, this is the same function. Okay, we will see in the next example with the sine of x, it's not the same function, but in this case, because of the function we're choosing, these two operations remain the same. Okay, now in 5 we have f of the absolute value of x, so the absolute value of x squared. But we know, because of the properties of the absolute value of x, that this is just the same function. So this is what we get here. And in this case too, with the absolute value of x squared, you see these things are not the same, okay, in general. But in this case, the absolute value of x squared, because x squared is always going to be positive, this is the same function as in the origin. Okay, and finally, the positive part of f of x is just x squared, because x squared is a positive function, well, a non-negative function, because it has 0 here. Okay, but if you take the positive function values, you will have the same as original. Okay, so now to the same thing, but with sine of x. Okay, so in this case, f is the sine of x. So again, for the first one, f of x plus c, you're shifting this function vertically, and in this case I'm shifting this function horizontally to the left. Okay, so I have this value here, it goes to here, this 0 goes here, then this 0 goes here. So it's not as easy to see it because this function is periodic, but you can see that it's shifted to the left. And now again, the curve is compressed when I multiply the argument. So this is sine of 3x. Okay, so in a sense, how to say this? If you have sine of 3x, if you focus on one period of the curve, okay, so the black curve goes from this to this. This is one period. So if you have sine of 3x, you will have three copies of that one. So you have one copy, 2 copy, 3 copies. Do you see? So it's 1 copy, 2 copies, 3 copies in the same interval. Okay, and this will be true for any periodic function. Whenever you multiply the argument, you are stacking multiple copies of the function inside the same interval. Okay, so this, then the fourth one, this is sine of 1 over x. So this is a very interesting function, because so when x goes to plus infinity or minus infinity, this thing goes to 0, so the sine goes to 0, so the argument goes to 0, so the sine of 0 is 0, so this gets closer and closer and closer and closer to 0, and this is go closer and closer and closer to 0. And then when the argument goes closer to 0, then this thing goes closer to infinity. But we know that the sine of infinity, so the sine when x gets greater and greater values, it just keeps oscillating, because that's just what the sine does. So what you will find here is, if you zoom in, is that you have oscillations that get closer and closer and closer and closer, and I'm going to show you now. So this is what it looks like. So as you can see, you can have an oscillation, but then it gets closer and closer and closer, and if I zoomed in here, I would still have these oscillations, and these oscillations go on forever. Okay. And actually you can't find a limit of this function when this goes to 0. Okay, there's no limit to this. Okay, so now 5 is the sine of the absolute value of x. Okay, so now a way to see this is the sine, the black line here, it's an odd function, we know this, so it's kind of a copy of this, but inverted again around the x-axis, right? But what we're doing with this operation is that we're making this function be even, actually. So what we're doing is copying this right hand side of the function and copying it here exactly. Okay, so that's why we start here and we copy it here. You see, it's the same function, but copied. So now the sine of the absolute value of x is an even function. Okay. Now this is the absolute value of the sine of x. It's a different thing, because this is just taking the absolute value. So whenever sine of x is negative, you just turn it positive. So it's just this positive mountains if you want. Okay, so you're having this. Okay, that's what you have, not the oscillation of the sine. Okay, now this is interesting. This is 1 over the sine of x. Okay, and so this means that when the sine of x goes to 0, then this goes to infinity. So these are the zeros. You have this goes to infinity and the 0 goes to infinity, and minus infinity when depending on the, well, it's not that, sorry, not plus or minus infinity, it's just that you have an asymptote here. Okay, so you have this kind of parabolas, if you want. Okay, so when sine of x is 1 over the sine is 1 again, and minus 1. Okay, so they touch, but then this guy goes to infinity, this goes to infinity. Okay, so you have this kind of parabolas, if you want. Okay, and finally, that's the positive part of the sign. So this is just the hill, and then 0 when it's negative, and then the hill, and then 0, and then like this. Okay. So as you can see, these operations, well, some of them are easy to see, so like the vertical and horizontal shift, or the contraction, or something like that. But when you start going on 1 over or x, or the sign of 1 over x, or the absolute values, these operations will do very different thing to the function depending on the function. So before with x squared, these two guys were the same, but and these two guys were the same. Now we have very different functions in the end because of the properties of the sign. Okay, and if you do it for different functions, you will find again that very different things appear. Okay, so that's it.